Okay, so all right. So last time we talked about the muscles and how the muscles are going to contract, starting from action potential or electrical signal moving down the nerve, going to the muscles. When it reaches the muscles, if you guys are following with me, the muscles are going, the signal is going to move down the T tubule, which is in between the two terminal cisternae. If that doesn't sound familiar, it means you're not following with me. You should be. So it runs down the T tubules. On either side of them, there is a terminal cisternae. Do you remember that? This part is the part that contains the calcium within the sarcoplasmic reticulum. It is part of the sarcoplasmic reticulum. So what's going to happen? Calcium will be released because of that, and the calcium will go find troponin, activating it, moving tropomyosin out of the active spots of the actin, which is the thin filaments, so that these heads of the myosin find the active sites of the actin, free the inner act, contract. This is the process. But now, what's before that? How did the electrical signal reach the muscle in the first place? So we talked about it when it already in the muscles, moving down the two tubules, right? This is what we covered. But what happened before that? How the electrical signal moved from the nerve to the muscle in the first place. So what's happening here is the electrical signal, first of all, is called action potential. This is the one that's going to move down, go through the T tubules and the rest of the stuff. So the membranes of the muscles, skeletal muscles specifically, is excitable. What's excitable? Excitable means it can be excited, meaning if something come to it, if a signal come to it, it's going to reverse its ions, generating an action potential. And this is what we're going to talk about. This part is hard, and this chapter, whole chapter, is the hardest of all chapters. So pay attention so we understand what's going on here. So neuromuscular junction. What's the neuromuscular junction? The name gave it away. Neuromuscular junction. The junction between the nerve and the muscle. Here is the nerve coming from the brain, carrying action potential signal going toward the muscles. When it go to the muscles, there is no touch. Are we following? It doesn't touch it. There is no touch. There is a gap in between. So there should be a way that the action potential, when it reach the end of the neuron, there should be a way to reach the muscles. And this is what we're talking about today. Okay, if I give you like a message and I told you, take this message to Canada, and you're taking your car and going all the way, and then you find the lake. Of course, you can't go with your car, right? So you have to find a boat or something, go to the other side, or a bridge, whatever. Let's say it's a boat. You should take the boat, go to the other side, give them the message, and then come back, right? So there is a gap in between the end of the neuron and the beginning of the muscle, and we will know how we can overcome this gap. And this is the neuromuscular junction, the junction between the end of the nerve and the beginning of the muscle. So what's actually going to happen here is when the signal come or reach the end of the neuron, it cannot jump. We know electrical signal doesn't jump, right? If I have electrical wire here and another wire here, it will not jump, right? So what are you going to do? That this electrical signal, when it reaches the end, it will do some changes in the end of the neuron and release a neurotransmitter. This is like the boat. The neurotransmitter, just like a boat, it's going to cross the gap for you, going to the muscles, making it changes in the muscles so that we will have electrical signal in the muscles. So this is the mediated part in between to overcome this gap. And this is called the neuromuscular junction. And the neurotransmitter here is called acetylcholine. Acetylcholine. Of course, you need to remember these names. So acetylcholine, what is it going to do? Here it is. Look at this here. This is the end of the neuron. The blue is the end of the neuron. Electrical signal come to the end of the neuron. What do we call this? Synaptic cleft. This gap here is called synaptic cleft. How can you cross this synaptic cleft? You cannot. Electricity cannot. It cannot cross a space. So what are you going to do here is, when the electrical signal reach this synaptic terminal, every single word that I'm saying is important. Otherwise, I would have skipped it or moved faster. But every word that I'm saying is important. So action potential is moving down the neuron. It reached the end. What's the name of the end? Synaptic terminals. Synaptic terminals, synaptic knobs. Same thing. Its terminals looks like a knob. Synaptic terminal, synaptic knob. So where are we right now in this blue? Synaptic terminal, synaptic knob. Electrical signal came here. It cannot jump. So what are we going to do? When the electrical signal come here, it will open gates for calcium right here on this membrane. Here, it will open the gates for calcium. Calcium will move into this synaptic knob. All right? Following? Electrical signal came to the end, cannot jump. What are you going to do instead? I'm going to open the gates for calcium. Calcium moves inside this blue. Calcium go to these vesicles. Vesicles like pockets or pouches. It will reach to it and will push it toward this edge right here. What is the red that we have inside of this? This is a neurotransmitter called acetylcholine. So calcium came in, go to the vesicles, push it so that it will be released. This is like dragging the boats towards the lake and then push it in. So the vesicles, when it's pushed by calcium, it's going to move towards this membrane and it will face the gap. So here it is, action potential reaching this, opening the gates for calcium. Calcium moving in, and look how it push it. Calcium is pushing it like this. Push it opened. When you push it like you're pushing a boat toward the water, it will then move in the water. So here it is, you push it, calcium pushing the vesicles, releasing its contents. And the contents are acetylcholine, which are these red spherical structures. It will be released in that space, which is the synaptic gap. This side, the blue, is the synaptic knob or the synaptic terminal, the end of the synaptic knob or terminal. The other side, which is the beginning of the muscle, is called motor end plate. Motor end plate. So what's a motor end plate? The beginning of the muscles. This is where, when you cross the gap, motor end plate is exactly the Canadian side. Okay, you move, cross it. When you reach the land, the Canadian side. Here it's called the motor end plate. So you are going to move down until you find, look at these, and this, and this. These are the receptors for this acetylcholine. So acetylcholine will move around until it finds these receptors and fit into these receptors. Look at this. See how this is fitting into this receptor? This is fitting into this receptor, and this too. You guys see this? So what will happen as a result of that? When it fit into this receptor, look at this, sodium will move into the motor end plate. All right? So what's good about that? Why sodium moving in will do something? Yes, this is exactly how we generate the electrical signal. This is how we generate the action potential. Sodium moves in. Normally, if this is a neuron like this, okay? There are ions outside and ions inside, okay? If you wanted to make an action potential or electrical signal, you have to move sodium in. When sodium moves in, it is changing. The electricity is changing because you're moving the positives in. What is a normal, stable for any muscle cells? The normal is, here is a neuron, here is a cell. Ions out, ions in. Positives and negatives are out, positives and negatives in. Everything inside and outside, it's there. We have sodium, potassium, calcium outside. We have sodium, potassium, calcium, and others inside. So what's the difference? The difference is it is not equal. There is a difference. The inside, normally, at rest, is negative as compared to the outside. Do you mean the inside is completely negative? No, I didn't say that. It's relatively. If you compare the inside of the cells to the outside, it is relatively negative. That's normal under resting condition. When you open the gates for sodium, sodium is positive. Are we aware of that? Sodium and potassium are positive cations. Calcium is negative. Okay, so what's happening here is sodium gates will open. Sodium start to move in. Isn't that changing the resting condition? It was negative inside compared to the outside. So what's happening when you move sodium in, adding positive in? This negativity will be moved out or will be eliminated. Okay? And when you do that, you are moving down to electrical signal. You're generating electrical signal. You will see the details, but just follow with me as we go. So far, electrical signal reached the end of the synaptic terminal, opening the gates for calcium. Calcium push these synaptic vesicles open like this, crossing the gap, go to the receptors, acetylcholine receptors, and then interacting with these receptors, as you see here, opening the gates for sodium. Sodium, when it goes in, action potential will be generated, and you did the job. You had action potential in a neuron, and your goal is to create action potential in the muscle, specifically the motor end plate, which is the beginning. And obviously, if you already have action potential, if you already have electrical signal, it will just move down the muscles, reaching the T tubules, pushing out calcium, releasing calcium, and the rest that you know. But I'm talking about this part specifically for now. Now, it's also important to know what is, yes. Yes, yeah, everything else is in the muscle. But how did you reach the muscle in the first place? So this is what we're talking about. So now, acetylcholine released from the vesicles, crossing the gap, interacting with the receptors, opening the gates for sodium, you generated the action potential. What is the fate of acetylcholine? We cannot leave it there. If you leave it there, it will stay stuck in the receptors and sodium continue moving in, moving in. You can't do that forever. You have to get rid of this acetylcholine. Look at the yellow. This is an enzyme. The yellow here is an enzyme that will break down acetylcholine. The name is also important. Acetylcholine esterase. It's the same name, acetylcholine. What's the enzyme break it? Acetylcholine esterase. Esterase, esterase. So it will break it down. And then what? It's called acetylcholine. Acetylcholine. Acetyl, cheap. We don't need it. Like if you get a bottle of Pepsi or something and you wanted to get the deposit back, you don't have to have the cover, right? You can throw it away and still get your money. Recycle. So the part that we recycle is the choline, not the acetyl, because choline is something expensive, something important. So this choline will return back right here. It will go back, and the synaptic knob will recycle it. It will add acetyl to it. So now it's ready. It will refill these vesicles, ready for the next cycle. Okay, so acetylcholine is an important enzyme that's going to do that work for you. Next is excitation contraction coupling. So did you overcome this gap? Yes, we generated action potential in the motor end plate, which is the beginning of the muscles. Then what? The action potential is in the muscles. The rest, we talked about it. Since it is in the muscles, it will find its way to the T tubules, which is part of the triad, and calcium will be released from the terminal cisternae. Terminal cisternae is part of the synaptic, part of the sarcoplasmic reticulum, I mean. So where is the calcium stored? Sarcoplasmic reticulum. Which part of the sarcoplasmic reticulum? Specifically, terminal cisternae. Yes, terminal cisternae is part of. It's part of the sarcoplasmic reticulum, and this is where we store the calcium, and it's also part of the triad, right? So now calcium is going to be released. It will find troponin, activating it. Troponin attached to tropomyosin. Tropomyosin was covering the active sites. When you push it away, the active sites are exposed. So now the heads of the myosin are going to interact with these active sites and doing like this. Look, here is myosin, here is actin. This is the active spot. Normally, the head always looking for the active sites. Once you find it, it will do like this, contract, okay? It will slide it. But what's preventing it from doing that is that active site is normally covered. So it's trying to reach out to the active site to push it, it cannot. You have to uncover the active sites. What's going to uncover it? This is what I just talked about. Calcium attaching to troponin, activating it, pushing away, troponin interact with tropomyosin, pushing it away, uncovering the active sites. Once the heads of the myosin find the active sites uncovered, it will push it, sliding it, which is contraction. So these are the steps that I talked about until it reached the contraction. Sarcomere is shorter. What's a sarcomere? When I ask you what's a sarcomere, what do you say? What is it? Just say it loud. I didn't hear you. From Z to Z. But what do you call it? What is this? The contractile unit of the muscle. This is the contractile unit of the muscle. Contractile unit, 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 unit. You have a lot of units. When all of them become shorter, the whole muscle contracting. So what is the sarcomere? Contractile unit of the muscles. You guys need to study your exams tomorrow. You have to know this. And I told you this chapter is hard. I know. But you have to know it anyway. It's part of the physiology. So yes, from Z to Z, sarcomere. Yes. But what is it? It is a contractile unit of the muscle. So by the end of this, you are going to do contraction, active site exposed, cross bridge. What's a cross bridge? The heads of the myosin interacting with the active sites when it is uncovered. We call that cross bridging. It cross the bridge, interact with the active sites and pushing it. This is called pivoting or power stroke. This, pivoting is this. Okay, you attach the active site, push it, slide it. Cross bridging, myosin reactivation, and moving it. So look at this picture right here. You will see the actin are these red or orange spherical structures. Okay, this is the actin. Here is a myosin head. You see this purple? This is a myosin head. The myosin head naturally always looking for the active sites of actin. Where are the active sites? Do you see yellow on this orange? Do you see yellow here? These parts right here, can we see it? This. These are the active sites. So here is myosin. Myosin trying to reach these active sites, all of these yellows. But look what's covering it, the blue, which is tropomyosin. And look at the troponin attached to it. So calcium comes, activates troponin, moving away tropomyosin. Now the active sites, the yellow, are going to be exposed. See how it's exposed now? You'll start to expose. Look, here it is. 1, 2, 3, 4. Can we see all of these exposed? The yellow. Now it's exposed. So the heads of myosin, once they see it exposed, they will interact with it, starting the cross bridging and the stroke. Look how it moves it. It's going to bend just like this, bending, pushing it. So this is the sliding of those two. This process is active. This process that I'm talking about right now, this, it's active. So you need energy that you get from ATP. ATP, when you break it down, what you get? ATP is a storage of energy, isn't it? When you break it down and take the energy, what's the product beside the energy? What you get? Here is ATP. I break it down, get the energy. What you end up having? ADP plus phosphate, right? And then what? And then when I get energy, I put it back, right? You put the phosphate back to the ADP, you get ATP back. Here is a cross bridging. You needed ATP. Then what? Then the heads are going to be released. Why the heads are released? The heads are going to be released because you did the contraction. What exactly make it released? Because calcium will not stay forever. It will leave troponin and go back to the sarcoplasmic reticulum, to the terminal cisternae, recycling. It will go back. Okay, so once it let go the troponin, it will let go the tropomyosin, and tropomyosin is going to recover these active sites. And this will be the relaxation. So once the heads of the myosin leave the active sites, relaxation starts. So what is this? What are we seeing here? What is this? What is this picture for? The whole thing. This is sarcomere. Red here is the Z. Here is the other Z. In the middle is middle line. Remember this? And here it is when it contracts. Look what's happening. It gets shorter. Compare this from here to here to this. This is the end result. Contraction makes sarcomere shorter. This is going to create tension on the muscles because you're pushing, sliding, acting over myosin like this, which is contraction. All sarcomeres become shorter. The whole muscle becomes shorter. And you did the contraction by creating tension between the ends of the muscles. This muscle has two ends, isn't it? If you follow it up, you will see one end here. Follow it down, the other end is here. The end that does not move is called origin. Look at this. Nothing changing, right? It's not moving. This is called origin. Look at this. Moving, right? This is called the insertion. So when the muscle contracts, create a tension, bringing the origin and insertion closer to each other. So you're going to bend a joint at the end. How long did this contraction stay? Like I can do like just like this. If I'm carrying something, I can stay some time, right? If I ask you carry my laptop and don't let it fall, you can carry it for a couple of minutes, right? Even more. What determined the duration of contraction? Duration of neural stimulus, like as long as you're sending signal, the contraction stay. Do you have enough calcium or not? If you don't have enough calcium, you know what's going to happen, right? Electrical signal come, T tubule, terminal cisternae, release calcium, no calcium to release. So no contraction, right? You have to have enough calcium. And this process of pivoting cross bridges, it needs ATP. You have to have the ATP. As long as you have these three, the contraction can continue. What's the fate of calcium? It will detach itself from troponin. Troponin is not active anymore. When troponin is not active, it will let go tropomyosin. Once you let go tropomyosin, it will go back and recover the active sites of actin. It will go back to the original positions. So now what? Now the active sites are covered. Can the heads interact if the active sites are not covered? If it is covered, it cannot, right? It will try to find it, but it's covered. So that's it. This is relaxation. Now there is a condition that we need to understand, which is called rigor mortis. Rigor means continuous contraction. Mortis, mortal, death. Right after death, there will be continuous contraction of the muscles because the ATP will run out and the ion will stop. The ion pumps that were releasing this calcium will stop working. So you're supposed to take calcium back, right? But it's dead. This person is dead. calcium cannot go back. It will stay. Continuous contraction for some time until you run out of ATP. So that simply explains when people die. If you ever see this, they usually close their mouth, right? Because if they don't and the mouth is opened, it will stay like this for some time, right? That's why they close it because of this rigor mortis. It will go away and the mouth will be closed, but it will stay for some time until they run out of ATP and until calcium goes away somehow. But this is called rigor mortis. Of course, you need to know what is this. Rigor, continuous contraction. Mortis, death. Reason, ATP pumps and calcium buildup. Um, this is the process again. Electrical signal come to the synaptic terminal, synaptic naps, pushing out the synaptic vesicles, releasing acetylcholine, crossing the gap, and generating action potential. Action potential reaches T tubules on either side of the triad, terminal cisternae. Releasing calcium will interact with troponin again and again and again. Troponin was going to move away tropomyosin out of the active sites. Active sites are exposed. Heads of the myosin reaching to the actin, contraction starts. And then what? And then acetylcholine is going to be broken down by acetylcholine esterase. Calcium go back to the terminal cisternae of the sarcoplasmic reticulum. Active sites are covered again. Contraction ends. The muscles relax. Now the amount of tension. Each muscle will do a different tension. Like this muscle, a strong muscle, can create this tension, okay? Muscle like this, strong. Other muscles like these muscles here are not. Every muscle produces certain tension. The tension is what make the muscles shorter and bringing the origin toward the insertion, or the insertion toward the origin. The insertion toward the origin. So what makes the muscle make more or less? I give you example here. Isn't it different when I carry my laptop like this versus if I'm carrying like a computer versus if I'm carrying the desk, right? Every one of those, they needs tension, right? I need less tension, less force to carry the laptop, but I need more tension to carry the computer, and I need more tension to carry a desk, right? The heavier it is, the more tension you need. So how can you like control the amount of tension? Yes. The number of power strokes, like how many of these interactions happening, the length of the muscle fiber at start. What does it mean? It means if this muscle is long like this from here to here, the amount of tension will be more than this muscle that's shorter. If you have a rubber band like this, okay, short, and you like stretch it like this and let it go, not much force. If I get a longer one and stretch it and let it go, right, it will make more force and more impact. The longer the starting length of the muscle fiber, the stronger and the more tension it produces. So the third one is frequency. If you want it more tension, give it more stimulation, which is the electrical signal. Stimulate more, more, more. The more you stimulate, the more muscle fibers work, giving you more tension. So this is what determines the amount of tension. Here is the length tension relationship. Simply, I told you already. The longer the starting length, the more the tension. That's it. Just like the rubber band. Short rubber band, long rubber band. Short rubber band, stretch, less force. Long rubber band, stretch, more force. Okay? The longer the starting length, the more the tension produced. Simple. So here is the whole thing. You start the contraction and you end until the relaxation, repeating the same thing over and over again. Now, when you do one muscle contraction, like you send the signal and you know the process now, are we good with this? electrical signal moving at the end, synaptic knob, pushing all that, right? Until you get the contraction. This cycle is called one contraction, and we call that twitch. Twitch is one contraction. Does it really happen like this? No. Usually, like if you're carrying something, how can you use just one twitch? Like one contraction and that's it. No, everything will fall down, right? We don't really do that. But I'm just giving you one contraction only. Just this one cycle, starting from the electrical signal until you contract, just once. We call that twitch. Practically speaking, we do more or several muscle contractions. Myogram, myo means muscles, gram means monitoring, and this is something that can be used to see the muscle tension if needed. So what are these twitches? A single twitch. Is it that simple? It is not simple. One twitch, this, just like, you know, when your eyes like do like this twitch, just close one of those. As simple as it looks, there are a lot of steps happening here. You start with the latent periods. Like I decided to contract. Do I contract right away? No. You decided to, you don't notice it, of course. You can say like, no, I decided to contract, here it is. It doesn't take any time. No. We measure it in milliseconds. Are we following? Did you get what I mean? Yes, I know that you decide to contract and you contract right away, but right away is time. It's even if it is a second, less than a second. But what's happening in this less than a second? There are details happening. The first thing is latent period. Latent period is what happened before you actually contract. Action potential move down the sarcolemma until the sarcoplasmic reticulum, specifically terminal cisternae, release calcium. What's happening during that time? Nothing. What happened to the muscles? Nothing yet, right? Did the muscle like do the pivoting and contract? Not yet. So this is called latent. So change without actual muscle contraction. No, it's always there. You have to have a latent period, which is the time that takes from the action potential reaching T tubules, terminal cisternae, releasing calcium until the calcium reach the troponin, tropomyosin. This period, it's milliseconds, but still counts. Now, when the calcium binds to the troponin, tropomyosin move away, starting this process of contraction, and then the relaxation. So it's not contraction relaxation. It's latent contraction relaxation. There is a latent period before that. And you understand now what happened during this latent period. Here is just a comparison between the different muscles and the amount of tension that you produced and how long can you stay. So like this muscle here, soleus muscle, we didn't do the muscles yet. You will see it. It's a muscle in your leg. Like if you stand up, if I ask you to stand up for half an hour, you can, right? You can, because you're using this muscle. It can sustain for quite some time. So stimulus come, look at this, stimulus come. And then here is a contraction red. Do you see this period here? In between the arrow, which is the stimulus, until you actually start the contraction. This is the latent period. And here is the actual contraction going up until you reach the maximum, and then you relax back. Now, do we actually do twitches like contraction, relaxation, and that's it? No, that's not practical. We usually get several contractions. So what if you give a signal, you start a contraction, and then another signal come? What's going to happen? The answer is it depends. It depends when it came, okay? Like this. If I ask you, carry this chair and put it here, and then I give you some time until you finish. Carry the next chair and put it here, and then I give you some time. You can do it, right? It's easy. But what if I ask you, like, carry this chair from here, and while you're moving, carry the next chair, carry the next chair. Okay, I will do it, but I have to move faster, right? If I go beyond that, you'll say, no, I can't do it, right? Carry this. You just carrying it, stop. carry this, carry this, carry this. You can't do it, right? So it all depends on when did I ask you to do it. When the action potential come to the muscle, at which stage? Did the muscle already latent period contract, relax at the end? That's easy, right? You will get one contraction, then another contraction. What if I ask you prematurely, earlier? It's different. How about you didn't finish relaxation yet? Different. How about just to start the relaxation and I give you another signal? Different. So what's going to be generated? It all depends on the frequency and when exactly did you give another signal. So the first thing is, the first one is the twitch. Look at this. Latent period, contraction, relaxation. I let it do everything. I'll let you do everything. Latent period, contraction, relaxation. Are you done? Yes. I give you another signal. This is twitch. Contraction, relaxation, twitch. Contraction, relaxation, another twitch. But what we actually need to know is, what if I don't wait for you all that time? What if I give you a signal prematurely? So the frequency is less than 50 per second. It's high frequency, but less than 50 per second. What's going to happen here is, which is something that happen in the cardiac muscles. That will give you a trepie. Trepie is like this. Contraction, relaxation. I didn't give you the time until the end. No, contraction, relaxation. You're about to finish. I'll give you another signal. The next one will be a little bit stronger. And the same thing. You go up, relaxing, relaxing. I didn't give you the chance to the end. You're about to finish relaxing. I'll give you another one. The next one will be higher. So go like this. Got it? Did you get this? This is called trepie. And trepie is simply every next contraction is stronger than the first one. Stair, step, increase. Stair, step, increase. And this happened when? Toward the end of the relaxation. If I give you another signal toward the end of the relaxation. How about if I go more than that? More than 50 per second. Like you started the relaxation and I didn't give you enough time. Not even toward the end. I will show you the graphs. But what if I do that? That will be a wave summation. It's not like this. It's not like stair steps. No, it will go more like this. I will show you the pictures. And this is called wave summation. Look at this. The first one is not in this picture. The first one is twitch. Latent, contract, relax. Are you done? Yes. Latent, contract, relax. These are twitches. All right for this? Look at this. The first one. Contract, relax, right before you end. I'll give you another signal. Right before you end. Right before you end. You see how it's going up? Until you reach the maximum and you will stay like this. This is called trepie. But the first part looks like a stair step, isn't it? It's going bigger, 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 bigger. Wave summation, you don't wait until the relaxation is almost gone. No. Like in the middle. Like this. Latent, contract. Relax in the middle. Not even at the end. In the middle. I give you another signal. This is called wave summation. It will go up faster. Okay? Because you give the signal about the middle of the relaxation. What if I do more than that? It will give you incomplete tetanus. What if which is, you just started the relaxation. This, contract, you just started the relaxation and I give you another signal. Are we following? Did you get this? And then I give you another signal. We'll go like this. Contract, about to relax, signal, 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 signal. It's not a flat line because you got a little bit of a time to relax. This is called incomplete tetanus. What if I don't give you any time to relax? You go like this, signal, 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 signal. You didn't relax at all. Signal, 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 signal. So what is this? No relaxation, completely, zero. This is called complete tetanus, which is contraction, and that's it. No relaxation, okay? This can happen only in the skeletal muscles. You cannot afford to do that in your heart. Why? Of course, we know this is common sense, right? The heart has to contract and relax. Even if you go faster, you still have to relax, get the blood in, contract, push the blood out, right? What if I relax and then I start to contract? No relaxation now, contraction, just like this. No blood will go in. That will lead to death. It does not happen. It cannot happen. Fortunately, the heart is protected. We will talk about it. But for now, I want you to get the 4 steps. The 4 steps are after the twitch. Twitch, TREPI, wave summation, incomplete tetanus, complete tetanus. Look at the incomplete tetanus here. You just started to relax, just started, and I give you another signal. Look at this. 0. I didn't even give you any chance to relax. 0 relaxation. This is complete tetanus. It will be something like this. No relaxation at all. Like this. Where is the relaxation? 0. This is complete tetanus. Now, this term, motor unit, is an important term. What's the motor unit? The motor unit is both of those processes combined. To remember, I started with what happened in the muscles first, and then I told you what happened in the neuron with the junction. If you put these together, we call that motor unit. Do not confuse that with motor end plate. This is completely different. Motor end plate is the beginning of the muscles only, but motor unit is a neuron with the muscle together. We call that the motor unit. We have many motor units to talk about. Another term which is called fasciculations. Fasciculation is involuntary muscle twitch. Okay? It's just, I think sometimes, like if you're nervous, don't you notice something like this? Involuntary. You didn't intend it to do it. It just happened. Yes, this is called fasciculation. Now recruitment. What's a recruitment? I just told you what is the motor unit. What's the motor unit? Are we following? Neuron and the muscle that this neuron work on, right? Neuron and its muscle, or its muscle fiber specifically. Neuron with its fiber. This neuron work on this fiber. It's not just one fiber. It can be a couple of fibers. But are we getting this? One neuron and one or more fibers. This one neuron go to these 3 fibers, let's say. What do I call this together? Motor unit. Got it? We have a lot of motor units in our muscles, and we do not utilize all of them at the same time. Isn't it better? Let's get practical now. If I recruit the whole entire class, and I'm asking all of you to do hard work, right? At certain time, everybody will be tired and you guys will say, no, we can't do it anymore, right? Instead, how about I divide this class into 5 or 4 groups? This group and this group will work, and the other two groups just don't do anything. Rest. You're tired? Yes. Okay. How about you? You guys do the work and you rest. Isn't that better? And it can stay for some time. This is exactly what's happening in recruitment. So what's happening here is I just need a little bit of contraction. Why should I use everything? Why should I use all my motor units? I don't need to, right? I can use part of my motor units. Let's say just random example. Let's say I have 100 motor units, all right? 100 motor units. If I'm carrying something like a pen, does that need a lot of muscles? Of course not, right? So how about I use 10 units only? 10 motor units, enough, right? And the 90 resting. How about I'm carrying something that's a little bit heavier than that? Well, I can recruit 20. What if I'm carrying the laptop? Maybe 40, right? How about a desktop? Maybe 60, 70. How about this desk, if I can carry it in the first place? 100. So what I'm doing here is I'm recruiting more and more and more. You can recruit 10, 20, 30, 50, until you get to the 100%. The 100% is the maximum that you can get, which is only if I have to. Something that's very heavy. Yes, I understand that I have to do it, but just like the weightlifters. Do you see the weightlifters when they carry the maximum that they can do, right? But they carry it for a second or two and they have to let it go, right? They do that right away. Because at this point, this is the maximum recruitment. If you give them something less than that and tell them keep carrying it, they can. Why? Because they are recruiting part and resting the other part. This part is tired. Okay, I'm going to recruit the other part, for example, right? So this is called recruitment. How many or how much of your motor units are you recruiting every time? Look at this picture right here. Look at the orange. The orange is a neuron that's feeding 6 or 7 fibers. And then you have the purple feeding another 6. And look at the blue, another 5 or 6. Okay, motor unit 1, 2, 3. I can use motor unit 1 if I'm carrying something light. It's something heavier. Okay, I'm gonna use 2, 3, right? If you use all of them, this is the maximum tension. And the process of utilizing part or more, this is called recruitment. And here is the maximum tension. If I use, of course, it's not 3, it's thousands. But this is just as an example. I can get the maximum if I recruit all my motor units. Muscle tone is a definition that you need to know, which is the normal tension at rest. There is a tension at rest. I'm not contracting. No, you didn't mean to do it. Here is what I mean. If I'm sitting down like this and relaxing, right? You would think that there is zero contraction in my muscles, right? I'm doing like this. Where is the contraction? No contraction, right? No, there is contraction. You don't feel it. There is a muscle tone that's always there as long as you are alive. There is a muscle tone, but I don't feel my muscles contracting. It is there, but less than what you can feel. There is always at rest. There is some muscle contraction. There is a tension. There is a firmness that you build on it. You don't go from scratch, not from zero, not like this 100% or zero contraction. No, it's not zero. There is 10% contraction or something, and you build on it. And this is called a muscle tone. The muscle tone is important for different things, like this is how we produce the heat, right? Muscle tones are pushing the blood. So muscle tone has to be there, and we only lose it after death. And that's explained, it's in the movies, but you know, when they wanted to know if somebody's dead or not, they hold like this and let it go. Did you see that? It's exaggerated, of course, but this is they mean the muscle tone. If it's completely zero, it's dead because we don't lose it. There is a muscle tone, even though it's minor, but still there. This is a muscle tone. Now, muscle contractions can be of different types. Every type is different. Like this, I can do this. I can push this, right? Pushing it like this, away, right? And I can pull it. This is something different. Or I can push this and it doesn't move, right? Can I move it? No. Is it moving away from me? If I push it? The distance still the same, right? But how about this? It's moving away, isn't it? The distance is different. So these are the two types of contractions called isotonic and isometric. Iso means, what's iso? Hmm? Same, yes. So isotonic, same tone. Isometric, same distance. It cannot be both of them. It's either isotonic or isometric. What do you think this is? I'm pushing it. Isometric, but is the tone the same? No, if you put your hand on my muscles, relaxing, you're contracting, you're pushing more tension, more tension, more tension. The tone is different, isn't it? But the distance changed? No, you call that isometric. The tone is changing, so it's not isotonic, but it is isometric. Clear? How about this? If I push this and you put your hand on my muscles, muscles are contraction, same contraction doesn't change. Pushing, 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 same tone, same tone, same tone. But isn't the distance changing? So this is isotonic. Isotonic. The tone is the same, but the distance is changing. Did you get this? Clear? However, this, look, this is isotonic. I'm moving it toward me, and this is also isotonic. The only thing changing here is the distance, isn't it? It's different when you pull something to you. I know it's both isotonic. The tone changing, the tone is fixed, but the distance is changing, isn't it? Did you get it? This is different than this. In both cases, the matrix is changing, isn't it? Moving away, moving close. Yes, this is changing. So this is not isometric, right? But the tone is the same. Feel it? Here is the tone. Same, 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 same. But they have two different names. If you're moving it towards you, it's different than when you move it away. Both are isotonic. Yes, it's subclassification. Okay, so there is isotonic, and this is isotonic is what I'm talking about. And there is concentric and eccentric. This is what I was talking about. Concentric or eccentric. Both of them isotonic? Yes. But isn't it different when I move toward me or away from me? This is called flexion. I'm flexing muscle, right? I'm moving toward me. And this is called extension. I'm moving away. Yes, both of them are isotonic. Both of them, the metrics are changing. But the subtype is if you move toward you, this is called concentric. And if you move away, this is called eccentric. When do they happen? It depends on the weight. If I give you something, look at this. If I give you something to carry, and this is not too heavy, you can do this, right? I ask you, like, contract. You can do that easily, right? But what if I give you something that's very heavy? You will go like this, right? You're trying, you're contracting, but you cannot. It will move away. We call that eccentric because in this case, the load is more than the tension. If the load is more than the tension, eccentric. If the load is less, you can do it. So this is called concentric. Okay. So what do you think this is? Isometric or isotonic? Isotonic. You see the metrics are changing? Oops. And this is isometric or isotonic? Where is the metrics? Measure from here to here, measure from here to here. Isn't it different? So it's not isometric. Isotonic. Is that eccentric or eccentric? Concentric or eccentric? Yes, because it's moving away. And this 6 kilograms is heavier than what you can afford or you can carry. Here is isometric contraction. The metrics doesn't change. The tone does. Here it is. Do you see any change in the distance from this to this? No, but do you see this muscle is more tension than this? The other thing is the load determine the speed of contraction. If you're carrying something that's very heavy, you can just like this, right? But if you're carrying something that's very heavy, right, it takes you time. So how fast depend on the load. Now relaxation, how do we relax? Not from the microscopic point of view. Relaxing in the microscopic point of view is when the calcium go back, letting go the troponin letting go the tropomyosin, recovering the active sites. Yes, this is inside. But in the muscles itself, on the gross level, what's happening here? Number one, elastic forces. Because when you contract, after you finish contraction, there is elastic forces. It's because you're forcing it out of its normal tension. So it goes like elasticity, move it back. The other thing is, look at this. I'm contracting, okay? And then I'm going to relax. What are the factors helping me? Contraction. Now this is not normal for my tendons, right? There is elasticity that will move it back. This is only one. How about this? Contraction, relaxation. Isn't the gravity helping too? Right? Let it go. The gravity is helping, isn't it? Number three, this muscle, biceps, there is a muscle here in the back called triceps. It's the opposing muscle. So this will also help. Look, I'm contracting now. Relax. This muscle is pulling it. So there are three factors that help the relaxation. We know that the contraction is active process, so we need ATP, and you know how to get the ATP. But there is something here additional. What do we use for energy source? ATP. Are we all familiar with that? We're good. What is our energy source in the whole entire body? ATP. This is the usable form of storing energy. I need energy. Get the ATP, break it down, take the energy. You end up having phosphate and ADP. Is that clear? I got more energy now. After eating, I got a lot of energy. What I'm going to do, put them back. Clear? Clear? This is the usable form of energy. However, there is an additional form, but not a usable form. Meaning, do you drink water or ice? Can you drink ice? But isn't the ice can be a source of water, right? So the usable form is water, right? I can drink water, but I can store some ice. We run out of water. We have zero water. That's okay. I'll take the ice out, melt it, make it water, and drink it, right? Here, the water is the ATP. This is the usable form of energy. The other form compared to the ice is called creatinine phosphate. Creatinine phosphate. Creatinine phosphate, can I use creatinine phosphate as a source of energy? No, it's a storage. So what if I need energy? I'm running out of energy. Yes, you can take that energy from the CP or creatinine phosphate and change it into ATP and then use it. Clear? Just like changing the ice in the water and drink it. You change the CP into ATP and use it. Is that clear? Clear? If you need this energy, there is an enzyme called creatine phosphate or CK, and this is an enzyme that will break it down, get the energy from there, change it into ATP, use it. So this is a storage form. And if did you guys ever heard about this? Like somebody is having heart attack and they do ECG. Did you see sometimes that they get blood sample and they measure something else? This is what they are measuring, the CK or CPK, this. Because this should be stored in the muscles, right? Where do I have this form? Creatine phosphate, I have it in the muscles, isn't it? In the muscles. It's helping in the muscles. Where else do you have it? It's just in the muscles, right? So what if I see it in the blood? It means the muscles are broken and it's released out, isn't it? Right? If I store oven cleaner in this bottle, and then I see oven cleaner in the ground, you know that this bottle is broken, isn't it? Right? So this is what they do. If they got a blood sample and they measure this enzyme and you see it actually in the blood increasing, they will tell you you have a real issue. In this case, maybe it's heart attack. How did you know? Because you're having a lot of CPK or CK in your blood. Why this is abnormal? It's not supposed to be in the blood. It should be in the muscles. It means your muscles are broken down, right? Which muscles are we talking about in this case? The heart, right? If you're interested to know what they are doing, this is what they actually do. It's not supposed to be high in the blood. Okay. There is another enzyme beside the CK. Uh, I don't remember right now. It's one of the isozymes, but I don't remember the name right now. But I can tell you about it. But it's the same idea. It should be stored in the muscles. It should not be in the blood. Once it's in the blood, the muscles are broken. Muscles are broken, like muscles of the heart are broken. It means uh, infarction or a heart attack. Okay. So ATP. How did we get that ATP from? I get the energy and put it in the form of ATP. Yes. Where did you get it from? From metabolism, or you break down the glucose that you get, you break it down and get energy out of it. Why are you eating in the first place? Think about it. Why are we eating in the first place? Because what I eat, I'm going to burn it and get energy out of it. Without energy, we die, right? Plus, we need the other components as well. And that's why we eat, right? But the main part is I'm going to eat. What I'm eating will go to the cells. I will burn it and get energy out of it. Okay? This burning process is goes in three levels or three steps. The first one that happen in the cytoplasm is called glycolysis. And glycolysis is glyco and lysis. What's glyco? Glucose or sugar. What's lysis? Breakdown. So glycolysis or glycolysis means you break down glucose. Okay? Into what? Glucose is 6 carbon sugar. I'm not talking about the details, just 6 carbon sugars plus plus, okay? 6 carbon sugar. Glycolysis is just like this. 6 carbon sugar, break it down into 3, 3. What do you call it? Pyruvic acid. 2 pyruvic acid. That's it. Because of doing that, you get a little bit of energy. Because you didn't do much. You just 6 carbon split, 3 and 3 carbon. Pyruvic acid, pyruvic acid. This process is called glycolysis, and it gives you 2 ATPs only. Okay? How about this pyruvic acid? Is that something that still have energy? Of course, it have a lot. This is like you get a piece of chicken and you just eat part of it and put it aside. This is still there, right? Pyruvic acid. Pyruvic acid still have a lot. But this process that happens in the cytoplasm, which is called glycolysis, it gives you two ATPs, but the good thing is it doesn't need oxygen. And that's why we call it anaerobic. Anaerobic. If we do have oxygen, we are going to use more steps. This organelle will not work without oxygen. What is the organelle I'm talking about? What's the organelle that does not work without oxygen? Yes, mitochondria. Yes. So here is glucose go into the cells. In a cytoplasm, glycolysis, you have 2 pyruvic acid, you got 2 ATPs. Did I use oxygen? No. Those pyruvic acid go to the mitochondria, if the mitochondria have oxygen, and you're going to do another 2 cycles, tricarboxylic acid cycle and electron transport chain, but these 2 cycles, you have to do it in the mitochondria, in the presence of oxygen. We call it aerobic, okay? And the aerobic will also use fatty acids, and this is a good thing about exercise. Don't you lose weight when you exercise? Right? Because you use your glucose, but then you break down the fatty acids as well. So look at this. Here is glucose going into the cells, okay? If you have oxygen, the mitochondria will work like resting. When you're resting, you get enough oxygen? Of course, right? I'm sitting down, I can breathe, I can get my oxygen as much as I need to, right? If I started to do a little bit of exercise, you're going faster. It's not easy to get all your needs from oxygen, right? What if I'm doing strenuous exercise? You're not getting enough oxygen for sure, right? What happened if you're using the treadmill? What happened to you right after if you're going fast? What happened after right after you step out of it? You step when you step down, what happened? Don't you go like for some time and until you rest, right? Right? Why? Because when you go like too fast, strenuous exercise, you don't have enough time to get your oxygen. So what are we using for energy? It all depends on oxygen. At rest, you have plenty of oxygen, all the oxygen you need. You're not even exercising. The oxygen is all over the place. So you get oxygen, and if that's the case, you're going to say, you know what? Why should I have oxygen? Why should I use like glucose and split it into two? I'm not forced to do that. I have oxygen. My mitochondria is working. Why don't I use fatty acid and just keep my glucose in the site? I'm not forced to use it, right? Because if you use it, this is not an advantage. This is not something good. Because glucose split pyruvic acid 2 ATPs. I can get 38 ATPs. Why should I do that, right? So if you do have oxygen, your mitochondria is working, and mitochondria can consume fatty acid and just put the glucose to the side. What do you mean put it to the side? I mean change it into a bigger molecule called glycogen. You have glucose. Are you going to use it? Do I have oxygen? Yes. I'm not going to use it. Why should I use it? I have oxygen. I can use my fatty acid, right? Which is good. Fatty acid, you're losing weight, you're sparing your glucose. The glucose is very easy to use, okay? Why should I use it? My mitochondria is working. So what should I do with the glucose? Just store it in the form of glycogen, which is a big molecule of glucose. Put it to the side and you will ultimately need it, okay? But at this point, no, I'm not going to use it, okay? How about if I'm doing moderate exercise? Can I use my mitochondria? Yes, but not as much. What should I do now? I'm going to compensate for this short of the work of the mitochondria by using some glucose. Clear? Am I still using fatty acid? Yes, but not as much. Moderate exercise. Strenuous exercise. I don't have enough oxygen at all. Clear? I don't have enough oxygen. You're doing like this, trying to get any oxygen, but you don't get much. So now I will say, no, I can't use the fatty acid. I cannot. I don't have enough oxygen for that. So unfortunately, the glucose that I was storing and I was keeping it until I'm forced, I will have to use it at this point. Okay? So now you're getting glucose, changing it into pyruvic acid, and normally pyruvic acid will go into the mitochondria and you get more energy out of it. But in this case, I can't do that. I get the pyruvic acid, glycolysis. Now I have pyruvic acid. Can I use it further? No, the mitochondria is not working. So you cannot send it to the mitochondria. But if that's the case, I'm going to get only 2 ATPs. Yes, do you have any other options? Do you have options? You don't have options. Your mitochondria is not working. Can I use fatty acid? No. Can I get the pyruvic acid and break it down further? No. Mitochondria doesn't work without oxygen. So if that's the case, that's going to help you a little bit. You get the glucose, split it. That will give me 2 ATPs only. Well, you don't have other options. Use it temporarily because you're doing strenuous exercise. One issue, you're not using the fatty acid. This is like a cheap source. You can't use it, right? I'm using my glucose, which is the expensive, right? I have to use it. Number two, I get 2 ATPs only. Number three, which is even worse, that the end product, if you don't use this pyruvic acid, if you keep on doing that, the cells are going to die. Why? Get glucose into the cells, split it into pyruvic acid, put it to the side. Another glucose, split pyruvic acid. Are you using this pyruvic acid? No, the mitochondria is not working. Are we following? Did you get what I'm talking about? Glucose get into the cells, split to pyruvic acid. Can I use this pyruvic acid for anything? No, the mitochondria is not working. Store it. Another glucose, store it. Another glucose, store it. The cells ultimately will be filled with pyruvic acid. No more glucose, no more energy, death. Does that actually happen? No, we are doing something temporarily, changing the pyruvic acid into lactic acid and move it out of the cells. So you empty a space for another glucose. Is that clear? So what's the problem now? The problem is I'm accumulating lactic acid. Lactic what? Acid. So what's the issue? Acidosis. Acidosis. Lactic acid. Acidosis. So what happened to you if you're strenuous exercise? Strenuous exercise. Aren't you forced to stop at certain point? You are forced to stop, right? You can't continue like this because lactic acid accumulating and it will start to hurt you. Okay, it will give you some pain and others, and because of the lactic acidosis. So you do need some recovery periods in order to the muscles to relax, and at the same time, this lactic acid that accumulated later, you will change it back to pyruvic acid. Okay, did you get my idea? Change it back to pyruvic acid because now your mitochondria start to work, so give it back. So you take it out temporarily. Pyruvic acid accumulate. The cells are going to be filled out. Okay? Can I continue like this? No. The cell will be full. So what should I do now? Get pyruvic acid in the form of lactic acid, move it out of the cells. Emptying a space temporarily for another glucose. Split pyruvic acid. Change it to lactic acid, take it out. Take another glucose and so on, as long as you're doing strenuous exercise. How about this lactic acid that I took it out here? You can convert it back to pyruvic acid or glucose when your mitochondria start to work. We call this cycle Curi cycle. So if I ask what's Curi cycle, this is what take the lactic acid and convert it back to pyruvate or glucose. Curi cycle. Oxygen debt is just what I talked about. What's oxygen debt? When you step out of the treadmill, what's going to happen here? You continue for a few seconds, for half a minute, right? Did you try before? When you step out, you continue to do that because you're recovering your debt until you you get enough oxygen and now you calm down, right? This period is called oxygen debt. Okay, you have a debt of oxygen, you don't get, your needs exceed what you're getting. Temporarily, you'll be breathing faster and deeper until you recover your oxygen. Heat production, this is something that happened automatically. About 2/3 of the energy generated in the muscles will be converted into heat, whether you like it or not. All this energy, a good part of it, about 2/3 or more, automatically will change into heat. If that's not the case, your body temperature will drop and you cannot take it. This is called hypothermia. Are we following? A good bulk of the energy will automatically change into heat to keep your body temperature. Effect of some hormones on the muscles. You need to know these four: growth hormone, testosterone, thyroid hormone, and epinephrine. All of these increase the metabolic activities of the muscles. Growth hormone, the name gave it away, grow, stimulate the muscles to grow. Testosterone, to remember it, men have more muscles than women, right? Males have more muscles than females because of the testosterone effect on the muscles. Thyroid hormone, stimulate the metabolism. Epinephrine, stimulate the metabolism. For the muscle performance, there is force and endurance. These are two different things. Force is the maximum tension that you can produce. Endurance is sustainability. Isn't it two different things? Some of your muscles can produce strong tension, strong force, but for a short period of time. Other muscles can give you less tension, but you can sustain, right? Like this muscle here, I can use it all of a sudden. It's very strong, but it doesn't sustain much. Compare that to your soleus muscle I was talking about in your lower limb. It does not produce that much tension, but you can stand up for a half an hour. right? This is called endurance. And for your information, both of those are not like fixed for life. You can actually work on it, okay? You can change it. You can improve your force and endurance by uh, physical conditioning, right? Example, endurance. I can walk for half a mile, I get really tired and I stop. How about if I do tomorrow and another time? Doesn't improve? Instead of walking for half a mile, I can improve my endurance for 3/4 of a mile, a mile, 2 miles, right? You can do that. This is called physical conditioning. Types of muscle fibers. There are three types of muscle fibers that we need to know. Not all muscle fibers are the same. There are fast, slow, and intermediate. Fast, these are the majority, and these ones because they are fast because they have large diameter. And when we say fast, fast to contract, but fast to get tired. Fast to contract, fast to get tired. The other ones that are slow, slow to contract, but slow to get tired. Get tired, we call it fatigue. Okay? Slow fibers, slow to contract, but slow to fatigue. Slow to contract, slow to fatigue. And these have small diameter. Intermediate is in between, mid-sized. The fast fibers, they found it to look white. Slow fibers, it looks red. Simply, some of us like chicken breast and some of us like the chicken thigh, right? Did you notice a difference in the color? Chicken breast is white, isn't it? And the chicken thigh is red, right? Simply, if you're eating chicken breast, know that you are using the fast fibers. And if you like the thigh, know that you are eating the chicken legs. Okay. How about this is in animals, right? Isn't it different? Chicken breast, white. Chicken legs, red, right? This is these are the two different types. But how about us? No, we have pink. We have in between. Humans have in between. Animals, yes, like chicken and others, yes, we do have uh, in the chicken they have white, red, but we humans have a mix. Did we get this part? Slow muscles. You got what you need to know about it? Slow muscles and fast muscles. Fast muscles, large diameter, fast to contract, but fast to fatigue, right? Slow, smaller muscles, small diameter, slow to contract, slow to fatigue, okay? And the color. Now there is something called hypertrophy and atrophy. Let me tell you that trophy is a Greek for building. Trophy is building. Atrophy means what's A? Without. So atrophy means without building, meaning the muscles shrink. What happens if you're doing your daily activities, your muscles will stay the same, right? If you exercise, your muscles get stronger and bigger, isn't it? How about if I'm laying down in bed for a month? Do you think my muscles will stay the same? It will become weak, which is called atrophy. Atrophy. How about the opposite? What if I'm exercising? My muscles get bigger and stronger, right? We call that hypertrophy. 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 More muscles building. So if I ask you this question, if I am like exercising, weightlifting, or something like this on a regular basis, and my muscles is getting bigger and bigger and bigger, what exactly is happening in there? Many things. Number one, my muscle fibers, same muscle fibers. How my muscle was like this and now it's like this. What changed? Many things changed. The diameter is increasing in that case because of the muscular contraction. The myofibrils, the number, is increasing. The mitochondria is also increasing. Okay, this explains what we see in the change of the shape of the muscles. With aging, obviously, everything deteriorates. Our muscles become smaller, weaker. It can actually become fibrotic, intolerance to exercise. Muscle fatigue is when the muscles cannot perform the work, right? I'm working, and then I get fatigued. That's it. You have to stop. The muscles are fatigued. What happened during fatigue? Metabolic reserve are gone. I mean, if you're using fatty acid, if you're using glucose, the glucose is gone. What are you going to do now, right? If you're exercising, your mitochondria is not working, right? You're using glycolysis, right? You run out of glucose. You have to stop, right? Metabolic reserves. Uh, you can actually go worse than that. You can damage your sarcolemma. Sarcolemma is the membrane of the muscle. You can damage it from overworking. And the sarcoplasmic reticulum. Your pH will go down. Does anybody know why pH goes down? Because of what? Which level? Not sodium. pH. pH. What does it mean when the pH goes down? Hydrogen ion gets more. So it's acidosis, isn't it? What leads to acidosis? I mentioned it like 10 minutes ago. Lactic acid, yes. It is lactic acid. Lactic acid. Endurance can change, both aerobic and anaerobic. Anaerobic is like weightlifting and 50-meter dash. Aerobic, which is prolonged activities, this sustained activities. You do something for a long time rather than using strenuous exercise. Cardiac muscles. Cardiac muscles are different than the skeletal muscles that we talked about. Cardiac muscles, of course, it's in the heart. Do you guys remember I told you that this is very important, and when you talked about the muscles, which is larger, comparing the three muscles: skeletal, cardiac, smooth muscles. Do you guys remember this? Skeletal, is it multinucleated or uninucleated? Multinucleated, because it comes from a group of myoblasts. Do you remember this? Is it striated or not? Striated. Cardiac muscles are also striated. So skeletal muscles and cardiac muscles both striated. Skeletal muscles are big, cardiac muscles are not. Skeletal muscles multinucleated, cardiac muscles are not. So cardiac muscles are small, short. There is no triad here. Do you remember the triad? It's a terminal cisternae with the T-tubule. This is not the case for the cardiac muscles. There is why there is no triad? What's the difference here? There is no terminal cisternae. Do you guys remember the triad? Do we remember the triad? The T-tubule, the two terminal cisternae. What if your sarcoplasmic reticulum does not have terminal cisternae? Do you still have a triad? No. Well, cardiac muscles do not have terminal cisternae. That's why they don't have the triad. Okay. What else is different? Single nucleus versus multi-nuclei. It work on aerobic metabolism, unlike the muscles can work anaerobic. They have something unique that's not in the skeletal muscles. Unique. It's something called intercalated disc. This is in the cardiac muscles. Intercalated disc. What's the intercalated disc? Remember when I told you with the recruitment that you can utilize motor units like 50%, 70%, right? You can do that. But for the heart, no. The whole heart contract, the whole heart relax. You cannot like contract part of it and the other part doesn't contract. The blood will not be pushed out, right? So what should I do now? If I wanted, like this is the blood in, you have to contract the whole entire heart or the whole entire ventricle. What should I do now? You have to link the cells together somehow. There is a disc that link them together so the electricity reach all of them at the same time. intercalated disc. A very important difference. This is a specialized connection between the cells so that all the muscle fibers contract at the same time. Look at this. Striated, but mononucleated or uninucleated. What else is different? Look at this. This is striated, isn't it? Look at this. Here is one compared to this, compared to this. Aren't these all striated, parallel? But look, striated and branching. Do you see the branching? It's branching. So skeletal muscles are striated? Yes. Cardiac muscles are striated? Yes, but branching. Striated plus branching. You will be asked about these differences. Do you see a triad here? Do you see a triad in this picture? This is the sarcoplasmic reticulum, the blue, right? Do you see terminal cisternae here? No terminal cisternae, right? So no triad. Cardiac muscles, unlike the skeletal muscles, they have automaticity. Do you contract your own heart? Do you ask your heart to contract all the time? No, it's working automatically. This is called automaticity because we have a pacemaker on the heart that's called SA node that generates the electricity automatically. You don't even think about it. You're sleeping. Your heart's still working, right? Because you have this SA node that generate your electricity. Last muscles are the smooth muscles. Where are the smooth muscles? You don't have to memorize. Is it skeletal muscles attached to the skeleton? If no, is it in the heart? No, that's it. Everything else in your body, smooth muscles. Clear? It goes without saying. We don't have to think about it. If I give you any example, just ask yourself, is it skeletal muscles? No. Is it in the heart? If no, that's it. Smooth muscles. Everywhere else. What's the difference between this and the other types? Remember the skeletal muscles? Large, striated. Cardiac muscles, small, striated branching. This is not striated and small, right? This is one. Multinucleated for the skeletal muscles, both cardiac and smooth, no. So what's the only one that's multinucleated? Skeletal muscles, because of their origin, okay? There is also a muscle tone with the skeletal, with the smooth muscle, same thing. And here is one of the differences. Calcium, and instead of tropomyosin, it binds to something called calmodulin. And this is something different. I'm focusing on just the important differences only. What's different here? Calcium attached to calmodulin. What did the calcium attach to in the skeletal muscles? Yes? Troponin. Troponin, but close enough. Troponin. Here, how about this? No, it's calmodulin. Calcium. Modulin, modulate. Calcium, calmodulin. Instead of, so I can ask you about this. Does the calcium attach to troponin in the smooth muscles? No, it's calmodulin. Calmodulin. Length tension relationship. There are no sarcomeres in the smooth muscles. It's not arranged in the form of sarcomere, so it's not directly related. They also have pace setters. They work automatically. Like when you eat, do you tell your esophagus or your intestine to contract and it's working automatically. There is something called pace setter, just like the pacemaker. And there is a muscle tone as well. That's it for this chapter.